Greetings and welcome to a new video. We continue with the determination or drawing of our Bode plot from a transfer function. So again, we start with an example here, and this will be our example number 3. And again, we will do everything step by step, the calculations, and verify these using MATLAB simulations. In this case, we will again see a complex poles, and also in addition, we will see double zero. So there will be also in addition that. So let's look at our problem, and the situation is given as follows. We have the system G, and we would like to draw the Bode plot of that. This is the system. We can see there's a double zero, and this is the complex pole for this system. So what are the steps? So the solution, the step 1, as we did in the previous videos, we rewrite each term normalized to a low frequency gain of unity. What does it mean? Now, before we move on to that, let's also set this in the standard form, which is for this complex expression. So we have this s squared plus 2 zeta omega n s plus omega n squared, which is a standard form for a second order expression or second order term. We have s squared plus 3.2s plus 16. So you can now recognize which term is, in this case, for example, the omega and also the zeta. You can also rewrite this in a form such that this is helpful for us drawing for our Bode plot by dividing actually each term by omega n squared. Now, if I now recognize this here, what we can say is the omega n squared is 16, so the omega n itself is 4, so the square root of 16. Now that is one of the parameters in this term. The other one is a damping ratio zeta, so that means 2 times the zeta times omega n is 3.2. So that means zeta is then 3.2 over 2 times omega n. Now if you substitute what we just have calculated, you will get for your damping ratio 0.4. Now that part is now done, and we will need these 2 parameters for our normalized low frequency gain of unity format in our transfer function. What we also need is we need to also set this in the standard form by actually taking out this 100. Since this is a square, that means we need to have this 100 squared out of this parentheses. Then you will get 100 squared times this term, so you will see s over 100 plus 1 quantity squared. Now you also take out the 16, so you will take out the 16. That's actually why we get here a 1. And you again recognize there is a zeta here, 0.4, and also the omega n. This is omega n squared. So everything is actually set here according to the standard form. Now we can simplify this, because 100 squared is 10,000 over 16 will be then 625, and the rest stays the same. Of course, this will be also 0.2. Now the step 2 is looking to our DC gain, if there is any. Sometimes you don't have the DC gain. For example, if you have a pole at the origin. And also the break frequency. We already have seen the break frequencies also before, but let's also repeat that here. The DC gain is directly what you actually determine from this transfer function by substituting s is equal to 0. So if you substitute s is equal to 0, this will be 1, this will go, and this will go. So you only also have 1 here in the denominator. So you will get actually 625 times 1 squared over 1, which is 625, which is actually shown here. Now we need to convert that in dBs. We will use this formula for that, and that will be then approximately 56 dBs or 55.9 dBs. Now the break frequency, we already have discussed this. We have double zero, which is real, and 2 zeros at 100 radians per second. We have complex poles. These are in pairs, and for that we have the damping ratio and also the natural frequency and also damping ratio calculated as shown here. Now for our magnitude plot, we need to have a lowest and a highest, let's say the limit for our frequency range. Now it begins at least 1 decade before the lowest frequency we have, and also it extends at least 1 decade above the high frequency we have. Now, what does it mean? In our case, we have the lowest frequency 4 radians per second and the highest frequency 100. That means actually for our beginning, we start then 10 times smaller of this one, so 0.4, and you go up to at least 10 times larger than that one, maybe 1000. So you actually plot at least between 0.4 and 1000. Of course, you can do also from 0.1 up to 10,000 or 1 million, but this is at least what you need to have a sort of a more accurate plot and also a more complete plot. Okay, now the step 3 is determining the slopes and for specifically the magnitude for each pole and zero. So how much contribution I get for each pole and zero. So this is a description. This is already also discussed in the previous examples. What we see is here the first frequency, the omega n, and also our double zero. Now we know we start with the plot by looking at 1 decade below, so at 0.4, that is actually our starting point. This is the starting of the slope for the omega n, so this is actually the first break frequency, and the other break frequency will start at 100 radians per second. Now we know for the first order pole, the slope is minus 20 dB per decade. But if you have a second order pole, that will be then 2 times that value, so that will be then minus 40 dB per decade. So in the DC gain stays the same, so you will actually see before that it is just 0 dB per decade. But from here it has a slope of minus 40 dB per decade, and it keeps that slope up to higher frequencies, up to infinity. Now for the double zero, now for a zero, if you have a first order 1 0, that will have a slope of plus 20 dB per decade. And if you have a second order, it will have 2 times that. If you, for example, have a fifth order, it will have that 5 times that. So in our case, we start, of course, here. Before that, it has a slope of 0 dB per decade. So it starts with a 40 dB per decade slope at 100 radians per second. Now, if you now add all these values for each column, you will get this end result specifically just for the magnitude. Now let's bring up then the magnitude plot specifically only for this case. Now we will now discuss or draw the contribution for each break frequency. Now let's also point and designate here the values more accurately, and also designate the break frequencies for omega n and also our double zero here at 100. Now, this is our DC gain, which is 55.9 dB. That's actually this value. Now we know we start with this plot at 0.4, but in our case, we already started at actually 0.01, so much lower, and that is perfectly fine. Now this slope part up to 4 radians per second has a slope of 0 dB per decade. Yeah, we can also say the slope must be from 0.4 up to 4 radians per second, 0 dB per decade. That is true, so you can actually recognize this is 0.1, 0.2, 0.3, and 0.4. From there up to 4, the slope must be 0 dB per decade, but it's also true from lower frequencies to 4 radians per second. The next segment is actually the part from 4 to 400. Now, in order to draw that more accurately, I have designated actually another point, which is 40, because that is 1 decade above. So from 4 to 40 is 10 times. So I will then draw that line. I will, of course, start at 55.9 and go down to 15.9, because that is a decrease of 40 dBs if you increase your frequency 1 decade. So this is a slope of minus 40 dBs per decade. I have to go, of course, up to 100, so I have to extend this line, and that will then approach that 0 approximately. So that is then also the complete segment for the second part. Now the final one is from 100 radians per second up to higher frequencies, and you can see this slope is 0, and that will go down like that, and we reach actually this 0 dBs. And this is a slope and that will be also the final segment for the magnitude plot. This is what we call the asymptotic approximation. This will be, of course, a little bit different, in some sense also quite different if you have peaking or gain peaking in your plot, but we will discuss this in the simulation results. All right, now we have this, and then let's then also make that correction in the magnitude plot if there is any correction required, of course. Now we know that we have gain peaking, that is because there are complex poles. Now we know from the plot, normalized plots, that the zeta will have an effect of that on that gain peaking. So if your zeta is quite small, for example 0.1 or 0.2, you will have some gain peaking which needs to be also set here and will be corrected. So for underdamped second order terms, so complex poles, we need to do that, and then you need to correct at the natural radian frequency by actually adding this value. Now, how much I need to add depends on, of course, the zeta. Now we have this formula, minus 20 log 2 times the zeta. That is how much I have to correct for this asymptotic value. So we said 55.9, but we have, of course, for this system, the damping ratio of 0.4. So if I substitute this in here, I will get 1.94 dB. So approximately 2 dB I have to add here. So this is 55.9, which is our asymptotic line, and I have to add 1.94 dB up to this one. I will get then 57.84 dB. So it is a little bit higher, but it really depends on the zeta, but it's not 55.9. And we will also check this in the simulation, or you will see also that this is a quite close value as we have simulated. Okay, now let's move on to the next step, which is then the phase slope contribution due to each pole and zero. In a similar form as we did for the magnitude slope contribution, but now we have to do a little bit more accurately and also a little bit more bookkeeping, because for phase plots we need to have for each break frequency we need to look 1 decade below and 1 decade above in order to say where it starts and where it ends. Now for example 4 radians per second, it starts actually 1 decade below, so that's actually what you see here, 0.4, and it will end at 40, that is 10 times larger, so 1 decade above. It's actually shown here. Now for each order, for example for the poles, you will have a slope for the phase of minus 45 degrees per decade, and for the second order complex poles you will have minus 90 degrees per decade. That's actually shown here. So it starts here, it keeps that phase, but now it's ending and has 0 degrees per decade slope. That's just a contribution by these complex poles. Now the double zero, now for 1 0, pure real zero will have a slope for the phase of plus 45 degrees per decade. Now if you have a second order pole, so double zero, second order 0, that will have plus 90 degrees per decade slope. Now it will start here because it is 10 times smaller, so 1 decade below, that's actually here, and 1 decade above, that's actually at 1000. Now you can see again, this is 0, but this is plus 90, this is plus 90, and then it will now end here. So now we need to add these 2 rows, and we will see then the total contribution for the total slope. So minus 90 degrees, 0, plus 90 degrees, and again 0. Now we will also draw that in the phase plot. And this is the phase plot, the empty plot. We will now bring up, and again we will now consider each of these break frequencies and effect of that, and then add them up later on for the total phase plot. Now again, designating the break frequencies, the 0 and also the omega n, and also we start at 0.4. That's also interesting. And for our discussion, it is helpful also to draw the minus 90 and the plus 90 degrees lines here. Now, first start with the 0 phase, because we start with 0 degrees, because that is actually where you start. in this case, because there's no phase inversion due to the gain of the system, because there's no minus sign before the transfer function. You can also see that if you look at the transfer function itself. Now from here, from 0.4, so actually from lower frequency up to 0.4, that is just 0 degrees. But now we will see actually a decrease of minus 90 degrees per decade up to 10 radians per second. So I have to go actually down. Now this is actually the first segment, because that is easy, from 0.4 to 4, because that's again 1 decade above. So you need to go down by 90 degrees, and we can see that we started at 0 degrees and we go down to 90 degrees if you increase your frequency 1 decade. Of course, I have to extend this to 10 radians per second, so I have to now also add another one. So I just use again as a 0.40. That means again 1 decade above. That will then go down another 90 degrees. So it will go then to minus 180 degrees. So that's actually this part. That's just considering the omega n. And now it will, after that 40, it will then keep going with the slope of 0 degrees per decade. So again, for the omega n is equal to 4 radians per second, which is then due to that second order poles, for the complex poles. We start with 0 degrees per decade, keep that 90 degrees per decade after 0.4, and we will then stop at 40 radians per second, and then from 40 radians per second up to high frequencies, we will see that the slope is 0 degrees per decade. Now in a similar form, we do it for the double zero. This is for the complex pole, double zero. Now this is the dashed line, and the blue line, it is actually again 0 degrees up to 10, because then it starts, and then it's increasing by 90 degrees per decade. So that's actually this. So you can see 100 and 1000. So it is going up from 10 to 100 and from 100 to 1000. So it is 2 decades up, and I have to go from 0 degrees to plus 180 degrees. That's actually what you see here. And then after the 1000, it is again 0 degrees per decade. Now we need to add the separate contributions together to the full plot for our phase. So we will now also make that clear using another plot, which will then give you in green here. This is actually the plot here, and that is the separate contribution. So the blue and the pink line will make that the green line, and again we end up approximately minus 190 degrees, 130 degrees. We will now be a flat, because this goes up as the same speed as this goes down, and now only this line will contribute, because this one is flat. And now we have this line, and now we have again the final contribution. You can also, of course, draw this green line directly by looking at these 4 segments, but it's also a little bit easier to see how much contribution I will get for each segment, and then the total contribution. So you have components, those are the complex poles and the double zero, and actually the total effect of it. This is now the phase plot, again in asymptotic approximation. Okay, now the final, again, the plot now in solid line, the green, and you can see this is now our final plot. Okay, and this will be of course checked in the simulation results. So let's move on to the simulation results and see what we get. This is of course the plot what we should get when we make that plot in MATLAB, for example. And you can see there are no asymptotic lines, but they are all curvy lines which are just smoothly going from one frequency to the other. And it is of course, that is what the actual expression will do. But we will use the asymptotic approximation to have an idea what's going on. And it is almost impossible to draw this line completely without going actually to the mathematical expression for the phase and also for the gain. That's not our purpose, but it will take a lot of time. The purpose of making those plots using asymptotic approximation is to have a very fast idea how that gain in a phase plot will look like. Okay, now we will now check the gain first. This is what we have from the simulation, and this is what we get actually what we have determined from our asymptotic approximation. Now you can see the highest, let's start with the DC gain. DC gain is 55.9, which is exact same as we have, so that is checked. We also see that the gain peaking here is 58.6, but we had 57.84. So it is not exactly as we have determined in our calculations, but it's close. So it is almost less than 1 dB off. So why is that happening? You might ask, okay, why is this not exactly that? Because this system is not pure second order. It has also some zeros that will have an effect on this value. So if you have a pure second order without any other poles or any other zeros, you will get exact the same value for your after your correction, after the correction is done. Now you can also see as a check, of course, this is due to the correction. For example, this part is due to that the complex pair of poles here, and we will need then a slope of minus 40 dBs per decade, or you will have 12 dBs, minus 12 dBs per octave. An octave means actually you increase your frequency by 2. So I have now labeled here 2 points in the gain. So this is actually 15 radians per second. This is the magnitude, 33.5. But if I go to the 30, so it's from 15 to 30 is 2 times. So there's a 1 octave above. This is actually just a check. I see now 21.8, and this is approximately 12 dB down. So this is then minus 12 dB approximately per octave. And that also confirms that this part is doing or behaving as a second order system. But you will get, of course, your zero, that's at 100, and you can see we have at 100 the flat line, which is just 0 dBs. But this says it is actually 6 dBs. And what's happening here? Now, for a break frequency, at that break frequency, you will have for the poles actually 3 dB lower than actual value, and for the zero you will get actually 3 dB higher than the actual value. That's for the poles and the zeros for a first order. So for each order you will get 3 dBs lower or 3 dBs higher depending on the zero or the pole. But if you have a second order pole, you will go down by 6 dB, or you will go up by 6 dB if you have a second order zero. That's exactly what's happening here. So at this pole, the zero location, we have estimated or have drawing using asymptotic approximation. It was just 0 dBs, but it is actually 6 dBs because that's actually twice that height of 3 dBs. And that's actually also confirmed by this plot. And then for high frequencies, the magnitude goes to approximately 0 dB, which is just as a scalar value 1. And you can also see that here in our plot. So that's actually a nice confirmation of our drawing and our simulation result. Of course, the gain peaking is a little bit less than what we have, higher than what we have estimated, but that is due to the zero we have here, and because it is not a pure second order system. Okay, now let's move on to the next one, which is the comparison of the plot for the phase we have from the simulation, also what we have drawing from the phase plot using, again, asymptotic approximation. Now, without going into the details, just looking at the shape of this actual curve for the phase and also the shape of our curve, we can see it looks quite similar. You might ask, okay, why? Now let's pinpoint some points at this frequency. Let's say at very low frequencies, this is approximately 0 degrees, and we also have that. So quite okay. We also see actually this is let's say lowest phase, which is minus 150. We have minus 130, but it has the same shape. There is of course some difference because this curvy line, it is not doing this is actually making some smooth transition from one point to another. And we also see it is again coming up and then will become 0 degrees. And it is also happening here for higher frequencies. And which you also see, for example, at 4 radians per second, which is the break frequency for the complex poles, it is approximately minus 58 degrees, and we had minus 9 degrees. Now, close enough, I think, for our quite crude approximation method. And we also see for the 100 radians per second, also minus 88, approximately minus 88, and it's also close to minus 90 degrees, so also pretty close what we have determined. Now for 1000, we have said, again due to that approximation, that it was 0 degrees, but in this case it is 11 or minus 11.2 approximately. And that is again due to that break frequency. So for each break frequency you will actually have a little bit lower or a little bit higher phase than in this case what we should draw. And due to that curving you will see actually a lower phase than actually what we have here. And that is, these are of course all determined in tables in several good control systems books. It's not our purpose to describe this in great detail there. You can of course read that for yourself in great detail. What we need to do is check our asymptotic approximation method with the actual plot, and if this is of course not matching at all with that, then we have done of course the wrong plot. But if you see that this is quite nicely overlapping this, then the plot is saying actually quite a lot about the actual system, and that's actually the purpose to have that Bode plot.